Now let's talk about the definition of the definite integral. So we just talked about Riemann sums for a number of rectangles n, and the idea that as you increase the number of rectangles, the approximation of the area under our curve improves. Now we'll consider sending the number of rectangles n to infinity. So to be precise here, we're going to assume that we have a function f of x that's continuous on the closed interval from a to b. As before, we're going to define delta x to be the length of the interval b minus a over n. Xk is going to be a plus k delta x, and xk star is going to be a representative of some point within the closed interval xk minus 1 to xk. In this instance, when we talk about the definite integral of f of x from x equals a to x equals b, what we mean here by definition is going to be the limit as n approaches infinity of the sum from k equals 1 to n of f of xk star times delta x. So just looking at what we are taking the limit of here, we're taking the limit of a Riemann sum. And the limit here focuses on n. So what we're doing is we're looking at the sum of the rectangle areas, and we're considering what happens as we chop that into more and more rectangles. So an important thing to consider here is that while the choice of xk star matters for what I've boxed in green, for instance, is it a left-hand sum or is it a right-hand sum, a midpoint, and so on, we saw before that we can get different approximations. As I send n to infinity, it doesn't matter which xk star value I choose in there. These are all going to approach the same thing, and that thing is what we call the definite integral. So with this in mind, one way I could use this right away is that if I need to use the definition to evaluate an integral, then I need to take my definite integral and kind of rewrite it in the form of what we have on the right-hand side in our definition. So we're trying to take this and interpret that as the left-hand side up here. And we want to rewrite it like the right-hand side. So we can take some general steps to get there. In particular, notice that a here is 1 and b is 4. So one thing I can do right away is find delta x. So if I have n rectangles, delta x is going to be b minus a over n, which in this instance is 3 over n. Then we can find xk, that's going to be a plus k delta x, where a here is 1, and delta x is 3 over n. So now what I need to do is, first of all, coming back up to the green box up here, we've found delta x so far, and we need to find the height of, say, our kth rectangle. Now we have a choice of xk star here. Like I said a moment ago, when I take the limit, it doesn't matter what choice we made. So let's just replace that with xk. So effectively, this would be finding the limit of a right-hand sum. If instead you chose a different scheme for your heights, you should get the same answer when you take the limit. So this means I'm going to take f of xk. What is f here? Well, f of x is the integrand, we call it, the function 2 minus x. So if f of x is 2 minus x, we want to find f of xk, or f of 1 plus 3k over n. So the function f takes in x and spits out 2 minus x. So now if the input is 1 plus 3k over n, the output's going to be 2 minus that. So simplifying this gives me 2 minus 1 is going to be 1, and then minus distributing that 3k over n. Now, we have f of xk, we have delta x, and what we're going to be able to say then is that the integral that we're trying to find is equal to the limit as n approaches infinity of the sum from k equals 1 to n of f of xk, which we found here. So I'm going to put that in 1 minus 3k over n times delta x, which we found up here to be 3 over n. So what I want to do here is evaluate this limit. And to do so, I really want to work my way from the inside out. That means I want to first figure out what this sum is, and then the last step is to take the limit as n goes to infinity. One thing I want to do right away is kind of distribute this 3 over n through here. So I can write this as the limit as n approaches infinity of the sum now of 3 over n minus the sum of 9k over n squared. And one thing that I'm going to do here is I'm going to break this sigma notation into two. So I have the sum here of 3 over n minus 9k over n squared. I'm going to write that as a difference of sums. So in particular, I'm going to take the sum of 3 over n minus the sum of 9k over n squared. Now, we're much closer to where we want to be. I want to go back to the prompt and point out that we were given a formula that we can use. So this is not something that you need to memorize by any means, but here we're told what we get when we find the sum from k equals 1 to n of k. Notice that I have something very close to that here. I have k in here, but it's multiplied by something that's not in my formula. Importantly, 9 over n squared is constant with respect to the summation index k. So we're going to be allowed to bring that not outside of the limit because it does depend on n, but I can bring it outside of my summation that has k as the index. So before we simplify this, let me do that one final step here. So much of this I'm not going to change, in particular this first part. I'm going to leave as is, and then I'm going to factor out 9 over n squared times, whoops, that should not be an infinity, times the sum here from k equals 1 to n of just k. So when I'm going to evaluate that part, I'm going to use this formula I boxed in orange. So I'm going to be able to replace this with n times n plus 1 over 2, which is given. So what does that leave me with? Well, I have the first part to deal with. I'm going to leave a blank here. And this is going to be this times what I have in orange. So for this first thing, notice that we have, put this maybe up here. I have the sum from k equals 1 to n of 3 over n. And notice that that, again, does not depend on k. So when I write out the terms here, I'm going to get, when k is 1, I get 3 over n. When k is 2, 3 over n. Essentially, I'm going to add 3 over n plus 3 over n plus 3 over n, etc. And I want to see how many terms are there. I'm summing from k equals 1 to n, so there are n terms. So if you think about, one of the things that makes this difficult is that we have n. Think about something that I add to itself. So if I take the number 2 and I add it to itself 10 times, well, the way we can think about that is we get 2 times 10. The same idea applies here. I have the number 3 over n. I'm adding it to itself n times. So the result is 3 over n times n, which of course we can just simplify to 3. Now we've gotten rid of the summation. This is just a limit question. And so as we go forward here, I really just want to think what happens here as I send n to infinity. Well, the limit of 3 is just 3. And notice what we have over in the second part. I have a polynomial up top of degree 2 and a polynomial in the bottom of degree 2. So when the degree matches, what we can see here is we get the ratio of leading coefficients, meaning that we're going to end up here with 3 minus that ratio of leading coefficients, 9 over 2. So we're going to end up with negative 3/2 for this. So I should also point out another way to end up with that 9/2 there is, of course, you could use L'Hopital's rule twice on that portion to get the 9/2. But we can take advantage of the fact that we have a polynomial over a polynomial. So this is just a demonstration of the way that we can use our definition of the definite integral to actually evaluate a definite integral. A lot of people misconstrue the definition with what's actually the fundamental theorem of calculus. And as we proceed, of course, we're going to make much more use of the fundamental theorem, say, than direct computations using the definition. But it's important to distinguish between these. The definition, the advantage that we have from the definition that we don't have from FTC, is that the definition has a very clear connection, for instance, to the idea that we're finding the area under the curve. It makes sense that we have rectangles that have areas that approximate that, and we can even see some visualizations to look at what happens as we increase the number of rectangles. FTC, which I've listed here, is much easier to use and practice, but it's certainly not clear how this has anything to do with the area under the curve. What I won't go through here, but I will point out, is that we can prove this theorem using our definition. So they're very much related. And so to be clear, as long as my integrand, the function I'm trying to integrate, is continuous, we're saying that a way that we can evaluate the definite integral from a to b of that continuous function is to take an antiderivative of it and look at the difference of that function evaluated at the endpoints. So if I come back to the very same example we just looked at and instead use FTC, then what I really need to do is I need to be able to come up with an antiderivative of 2 minus x. And by that, I'm saying we need to think of a function such that when we differentiate it, we get 2 minus x. So a function that differentiates to 2 would be, for instance, 2x. And for x, we could use x squared over 2. We're going to evaluate this from x equals 1 to 4. And in doing so, we're going to get 2 times 4 will be 8 minus 4 squared over 2, which is 16 over 2. Then we will subtract, when we plug in 1, we'll get 2 minus 1/2. And sure enough, this cancels out. And we're going to end up with the same answer as we got before, but much, much quicker. So given the choice here, certainly it would be much more efficient to use this method. But it's very important in general in math to always have a very good understanding of our definitions before we come up with maybe ways that we use more efficiently in practice. And then the last thing, kind of tying these two things together, is we can connect these, that if I'm asked to evaluate a limit, but this idea with the nudge here of using FTC, if I can identify that this limit I have here, which certainly finding that limit is not necessarily an easy thing to do, if I can identify that that can be expressed as a definite integral, and then I now have this quicker way of evaluating definite integrals, it gives me then a quicker way to evaluate this limit. So this is how we can kind of put these two ideas together. So here, my process is kind of the opposite of what I did in this first example. There, I started with a definite integral, and then I rewrote it in this limit form. Here we want to go backwards. I want to try to figure out a function f of x in an interval a to b that so that I can rewrite this as the integral from a to b of that function f of x. So it's really important here, I think, to have kind of a way to chip away at the pieces that we need here. I'm trying to identify this part as f of x, k star, of course, but again, I'm just going to choose xk, delta x. So what I like to do to get started is I like to try to look for a suitable delta x. Remember that delta x is always a number over n. So looking at this here, there's certainly a product of two things, and one of those things is 1 over n. The other thing is the square of something. So right away, I see the 1 over n, and I think that makes sense to be my delta x. If that's delta x, a few things I can then say. So if that's delta x, that tells me that xk is a plus k delta x, or in this case then, k over n would be k delta x. So now I know what xk looks like. But the other thing I know, looking at the original term up there, if 1 over n is playing the role of delta x, then the other part, when it's multiplied by 2 plus 2k over n all squared, that must be the rest of what I need, f of xk. Since we know what xk is here, that must be f of a plus k over n. So looking at this, I have a few choices here. So notice that while I'm looking for a function f of x that will work, I'm also looking for a number a that works. And this is kind of interesting because what happens is that I'm looking for a pair, a function f of x and a constant a, so that I can match these things up. And it turns out you could choose any value you'd like for a, and there's going to be a suitable function f of x that you can choose to go with it. So to demonstrate that, I want to look at two different ways of setting this up. First of all, if we look at this here, one thing that we could do is we could just simply choose, maybe I'll call this choice 1. So one thing we could do is choose a to be 0. So what happens if we do that? If we choose a to be 0, then what I'm really doing is I'm taking 2 plus 2k over n, oops, 2 plus 2k over n, quantity squared, and I'm matching this up to f of 0 plus k over n, or just f of k over n. So when I'm looking at this, I'm trying to track where the input goes. So this function sends k over n there. That helps me then decide what would it do to x. So if I want to find the function f of x here, well, I can replace what I've boxed in green with x, and that's going to give me this function. So that means that the limit that we're starting with here, that we were trying to evaluate, we can say that that equals the integral of this function. And in particular, we now want to find what the bounds are. Well, notice that we chose a to be 0. So that's playing this role. Well, how do we find b? Remember that delta x as the numerator always has b minus a. So b minus a is 1. We know a is 0, so b has to be 1. So if I want to evaluate this limit, now I can use the fundamental theorem of calculus to evaluate this integral. So if we square this out, I'm going to have 4 plus 8x plus 4x squared. So using FTC, the antiderivative 4x plus 4x squared plus 4x cubed over 3. Evaluate this from 0 to 1. I'll get 4 plus 4 plus 4/3. And this will end up giving us 28 over 3. So this number is what our limit is equal to here. So this is a full solution. To point out that we could choose other things, I will say sometimes certain choices of A might make it harder to find your choice, your function that matches. But an alternative way I could have solved this is just to choose a different value of A. For instance, choose A equals 1. So kind of jumping up above this number 1 above that, we would have in this instance that we'd want to try to match this up to f of 1 plus k over n. So here I'd have to figure out what happens to this. And it's a little difficult in the current way that it's written to necessarily see that, but notice that it would be easier if I observed that what I have here is the same thing as 2 times the quantity 1 plus k over n, all squared. That's an equivalent way to write the left-hand side. And in doing so, I get a clear idea of what happens to 1 plus k over n. So this function would actually be the function f of x is equal to the quantity 2x squared, or 4 times x squared. So I would also be able to say that the limit that we started with is equivalently equal to the integral of 4 times x squared. But importantly, my bounds are different. Here we chose a to be 1. The length of the interval from our delta x is still 1. So b would have to be 2 in this instance. And although this looks different, right? This is a different definite integral. What you should be able to check is that we get the same numerical answer when evaluating this here. And importantly, you could choose any value for a, and you'll get a paired function f of x, but these are all going to be equivalent expressions that give me the same numerical value for that limit. So kind of moving on from here, and where we'll head in this course is that it's not always so easy just to apply FTC. One of the things I used in this example and the one above was the ability to quickly find an antiderivative for the function we're trying to integrate. And that's not always the case. So what we'll move on to considering is some different integration techniques that will help us to get to that antiderivative so that we can plug in the endpoints and subtract.